What's up guys, and welcome to this video. In the previous video we went over impulse, specifically in terms of this F net equals delta P over T equation, which we found very useful, and we used to solve some questions specifically to do with bullets. But obviously it can be expanded beyond bullets to things like car crashes and all of those things, but a common example especially in school, are these bullet questions. But now we're going on to more of these theoretical kind of questions. Okay, so the focus point on all of these questions are the following equation: F net equals delta P over delta T. Okay, and basically the question usually goes something like this. It says use the concept of impulse to explain. Okay, so let's go over, we'll probably do two examples, but let's start off with this example. Okay, so to explain the following. Okay, so seatbelts, why do seatbelts have some slack when they act on a passenger and are not rigid? Okay, so basically, if you think about it, when you're sitting in your car, if anyone has ever been or played with their seatbelt, if you're in an accident and basically you get flung forward, let's say, then the seatbelt actually gives a little. It lets a little bit of movement and then becomes rigid and stops you from moving. Okay, so if you've played with a seatbelt and you've felt it, if you tug it very quickly, if you tug your seatbelt very quickly, you can see that it actually slacks a little before it becomes stiff. Okay, so the question is why? This isn't a design flaw, but rather this has actually been designed in this way for a specific reason. And we can use impulse to explain this. Let's think about it, right? When you're in your car, or yeah, when you're in your car and you're traveling, let's say you're traveling at, initially traveling at velocity equals, let's say 120 kilometers per second. Then your final velocity, when you're in an accident of some sort, apologies for that, when you're in an accident of some sort, is 0 meters per second or kilometers per second, right? So then your impulse, or your delta P, equals mass times delta V. For both situations, when the seatbelt is rigid and when the seatbelt gives a little, the impulse is the same because the mass is the same, and in both situations, the change in velocity is the same. So therefore, the net force is dependent on time, because we already said that this is equal to a constant, right? So therefore F net equals some constant over delta T. So if delta T increases, F net decreases. If delta T decreases, F net increases. So by giving some slack, we're increasing this time. When your seatbelt gives a little, it increases the time over which you're experiencing this force, and that causes the force to go downwards. Okay, so formally, okay, so that's just a little bit of an informal explanation. Let's put that to a side. You don't have to explain it in this way, I mean, unless you really want to. But we could explain this by going into details such as the following. So to explain this, we can say that the impulse for when the seatbelt gives some slack or is rigid is the same. for both scenarios. Okay, so that would be your first point. Then we can say that when the seatbelt gives some slack, the time period is longer. And we can say using Fnet equals delta P over delta T, an increase in the time decreases the net force. Okay, so less force is experienced. So that's one way of explaining it. Okay, or that is how I would go about explaining it. Let's try explain another situation. Okay, so let's say Y is an egg dropped on a sponge, less likely to break than when it is dropped straight onto the ground. Okay, so let's try and explain this one. It follows a very similar procedure. So we can say that the impulse for both scenarios, I'm not going to name them, but for when there's a sponge and when there isn't, the impulse for both scenarios are the same, or is the same. Okay, when dropped onto a sponge, the time period, or the contact time, or yeah, we can say when dropped on a sponge, the time period is increased. Okay, then we can say using Fnet is equal to delta P over delta T, an increase in the time, an increase results in a decreased force on the egg, and therefore the egg is less likely to crack. Okay, so like I said before, they follow a very similar kind of framework. You just need to explain that the impulse for both situations is the same, but under certain circumstances the time period is increased. Then using our Fnet equals delta P over delta T, or Fnet equals impulse over change in time, by increasing the change in time, we are decreasing the force, and that has an effect on certain situations. Okay, so that basically covers impulse in its totality. And next, in the next video, we are going to do conservation of linear momentum, but that might be a entirely different series. So thanks for watching, guys. I hope you found this helpful, and I hope you understood everything.